theorem, and that's called the conjugate root theorem. So what the conjugate root theorem says is it says let p of x be a polynomial with rational coefficients, and then the irrational roots of our polynomial p of x come in conjugate pairs. And what that means is that if a plus the square root of b, which is an irrational root because of the square root symbol, is a root of a polynomial, then a minus the square root of b is automatically a root as well. And we saw this concept of conjugates back in our last unit with our imaginary conjugates. But we also have our complex conjugates. We also have these irrational conjugates that we can look at as well. Well, just like we had for your irrational ones, we also have this for imaginary roots as well. So if p of x is a polynomial now with real coefficients, then the imaginary roots of p of x come in conjugate pairs. Meaning if a plus bi is a root, then our complex conjugate of a minus bi is also a root. So let's see how we can use these in action. It's kind of like a puzzle that we're going to be figuring out. So in example 6, it says if a quartic polynomial p of x has the square root of 3 and 4 plus I as some of its roots, we want to find the remaining roots and write that polynomial in factored form. Well, let's start back at the beginning. What does it mean to be a quartic polynomial? So a quartic polynomial means that our degree is equal to 4, which means by the fundamental theorem of algebra, I need to have 4 roots. So quartic polynomial means degree 4. Fundamental theorem of algebra then tells me that I should have 4 roots. Well, I was only given 2 of these roots. I was given the square root of 3, and I was given 4 plus I. Now, I could maybe have some multiplicities. That could definitely happen. But the conjugate root theorem tells me that if I have any root of the form a plus the square root of b, then I also have to have a minus the square root of b. And if I have a plus bi, then I also have to have a minus bi. So just because root 3 is a root, that actually also tells me that negative root 3 is a root as well, using that conjugate root theorem. Here our a is equal to 0, and then our b is 3. Likewise, since 4 plus I is a root, that means that 4 minus I is also going to be a root, since our complex conjugates come in pairs. So now I actually have a total of 4 roots, which is exactly what I was looking for. So I want to write this polynomial p of x in factored form. Now remember, to go from roots to factored form, it would be x minus that root. So for the square root of 3, my corresponding factor will be x minus the square root of 3. Then for the negative square root of 3, it'd be x minus the negative square root, which would be just x plus the square root of 3. So there's our first 2 factors taken care of. Now for 4 plus I and 4 minus I, I've got to be careful here. I'm going to do x minus, but since my root itself has more than one term, I need to put another set of parentheses around it. So I end up with x minus 4 plus I, and then for the last one I'll get x minus, and then in parentheses, 4 minus I. Whoops, there we go, close our parentheses there. So when we have these complex roots, or if we have an irrational root with the a plus the square root part, then I want to make sure that I'm putting them in parentheses, because that negative sign would need to get distributed to both of them. Now if you want to distribute it, that's up to you, but I am okay if you guys leave your answer just like this, because they asked it for us in factored form. So I do not want us foiling anything out. I want us leaving this in factored form. Let's look at example 7. It says if a quintic polynomial p of x has 3, 5 minus the square root of 7, and negative 1 minus 3i as some of its roots, we want to find the remaining roots and write the polynomial in factored form. Well, start at the beginning. What does it mean to be a quintic polynomial? A quintic polynomial means that our degree is equal to 5, which based off of the fundamental theorem of algebra tells me I have to have 5 roots then. How many roots are we given? So in this example, we are given 3 roots so far. So the roots that we have are 3, we have 5 minus the square root of 7, and lastly we have -1 minus 3i. Now the conjugate root theorem only applies to irrational roots and our imaginary or our complex roots. So which ones of these are going to have a matching pair to it? So here only the 5 minus 7i will have a matching pair. That will be 5 plus the square root of 7, and then our imaginary root of -3 or -1 minus 3i will also have a matching pair of -1 plus 3i. The 3 itself does not have a pair because that's not an irrational and that's not an imaginary root. That is a rational root. So now we have our 5 roots, so we just need to write this out in factored form. So why don't you guys pause the video here and write out your factored form for example 7. So our factored form, if 3 is a root, x minus 3 is the factor. If 5 minus the square root of 7 is a factor, or is a root, then x minus, in parentheses, we have that 5 minus the square root of 7. We'll have to do that for the next 3 as well. So we get x minus, then in parentheses, 5 plus the square root of 7. And then for our last 2, we have x minus the -1 minus 3i in parentheses. And our last one would be x minus the -1 plus 3i in parentheses again. So for each one of these, because we have more than one term in our root, we have to make sure we have that extra set of parentheses in our factor. There is no need to FOIL it out. I do not want you guys to FOIL it out at all. Please leave this in factored form. Let's look at our last example of this type. So we've got in example 8, it says if a polynomial p of x has 7 minus 6i, 1 plus the square root of 11, and 13 as some of its roots, what is the minimum degree of this polynomial? And explain. So this is a little bit different here. We're not told what the degree is. Instead, we're trying to figure it out. Well, why don't we list our given roots? How many roots are we given in this problem? So we're given 3 roots. We have 7 minus 6i. We have 1 plus the square root of 11. And we also have 13. Those are our 3 given roots that we have. Based off of this, why don't you write out our list of what our other roots are going to be as well, using our conjugate root theorem that we have. So the other roots that we're going to be given is, since 7 minus 6i is a root, then 7 plus 6i has to be a root. And since 1 plus the square root of 11 is a root, then 1 minus the square root of 11 is also a root here. For 13, this is not an imaginary number or an irrational number, so we do not have another matching pair of roots that goes with it. What that means is we have 5 roots that I must have. I can't have any less than this. I have to have 5 roots at least, which tells me that my minimum degree then would have to be equal to 5. Oops, degree. And the reason that is we're using not only the conjugate root theorem, but we're also using the fundamental theorem of algebra, which says that the number of roots, or the degree, equals the number of roots. And so since I have to have at least 5 roots, my minimum degree would have to be 5. Now, I couldn't find my exact degree. I could only find kind of a minimum that I would have, because maybe there's other roots that they weren't giving me as well. But using the conjugate root theorem, any imaginary and any irrational root has to come with its conjugate. So for the 7 minus 6i, I have to have another root, and for the 1 plus the square root of 11, I have to have another root. Because of that, I have to have at least 5 roots, which means my minimum degree is equal to 5 then.